We've talked about substances dissolving in water, but to this point we haven't actually talked about how much is actually dissolving. Scientists need to know how much, and we need a way of expressing it, and this is where concentration of a solution comes in. We already know that we can describe the concentration of a solution in words. So for instance, we can talk about a solution as being concentrated if it has a lot of solid particles dissolved in it. We can also talk about a solution as being dilute if there's only a small amount of the solute dissolved in it. But this isn't very useful for us as scientists. We need to have some numerical way of measuring the solubility. There are a number of different ways of doing this. We could do it in terms of mass, we could do it in terms of percentages. In the old days, the British customs agents wanted to find a way of deciding whether a liquor was required to pay a tax, so they needed some method of proving whether it would attract a tax. To do that, they took a bowl full of gunpowder and they'd pour the liquor over the top of it. If they then put a match to it and the gunpowder exploded, then they would say that meant that the liquor had to pay a tax. Now it turns out that if the liquor had 57% alcohol, then it would explode, and that meant that it was 100% proof. So you can see how we can have Bundaberg rum, which is overproof, which is 120% proof, and that just means that the alcohol concentration is a lot higher. So in this case, we're describing the concentration as a percentage of the solution. So 57% of it is alcohol. But again, to do calculations like we want to do, that sort of number is not particularly useful. Melbourne Water measure their concentrations in terms of milligrams per litre. How many milligrams of the solid will dissolve in a litre of water? So for instance, if we look at particular dams, say for instance the Cardinia Dam, we can see that the fluoride concentration in milligrams per litre is 0.88 milligrams per litre. When we get down to things like cadmium, it's very much less. So this is a concentration that we can actually work with. We can do calculations in milligrams per litre. If we add a certain amount of solid to the water, we can work out how many milligrams will dissolve in a litre. If we increase the volume of the liquid, then we know that we can dissolve more of the solid in it. Of course, I've mentioned the concentration as being in milligrams per litre, but there's nothing to say that we have to have litres. We could have kilolitres or millilitres. So we need to be able to convert the volumes from one thing to the other. You remember in the metric system that from going from a litre to a kilolitre, it's 1,000 times bigger. So therefore, we have to divide it by 10 to the 3 if we want to work out how many, what the volume is in kilolitres, or the concentration is in per kilolitre. We would divide by it. You can see from these numbers here, going in one direction, we divide by 10 cubed, and going in the other direction, we multiply by 10 cubed. The number underneath here, looking at the concentration here, this concentration is written in grams per litre, but we could also express it in moles per litre. Now you remember, to go from grams to moles, we have to divide the grams by the relative molar mass, which is what is written down here. If we want to go the other way, from moles per litre to grams per litre, then we just have to multiply the number of moles by the molar mass of the particular substance that we're trying to dissolve. So to give you a practical example, have a look at this problem. We're calculating the concentration of salt in milligrams per litre in a 250 ml glass of salt water. So first of all, we need our formula. As I've said to you before, it is really important to write the formula down before you do anything else. So in this case, our concentration is just given as the mass of our substance divided by its volume, because we're wanting an answer in grams per litre. So we have to get our units correct. So first of all, we start off with our mass in grams, which is 3.2, and our volume, which was 250 mils. To turn that into litres, we have to divide that by 1,000, so we get 0.025. Once we do that division, we get 12.8 grams per litre. Now, if I wanted to turn that into milligrams per litre, there's 1,000 milligrams in a gram, so we just multiply that by 1,000 and we get 12,800 milligrams per litre. A number of times you boys have taken bottles out of your cupboards and seen that it has 0.2 m written on the side of it, and you've asked what 0.2 m means, and I've just said that's the molarity or the concentration of solution. Now we can understand what this actually means. In chemistry, the convention we have is that we can calculate the concentration in moles per litre of solution, and that's described as being the molarity. It has a number of symbols. We can either write it as mole per litre or mole litre to the -1 or just big M, which means exactly the same thing. So our formula for calculating the molarity or the concentration is just equal to the number of moles, which is N, divided by the volume, which is given in litres, and the concentration will then be in moles per litre or molar solution. We refer to that sometimes as 0.2 molar solution, which just means 0.2 moles per litre. So let's see how this works in practice. In this problem, we're asked to calculate the concentration in moles per litre of a solution, but we've been given milligrams and millilitres. So the first thing that we have to do to start this problem is to convert our units, because to calculate moles, we're going to need grams, and to calculate moles per litre, we're going to need our volume in litres. So the first step is to convert the units. 40 milligrams is 0.04 of a gram, and 325 mils divided by 1,000 to get it into litres. Please notice that the significant figures have to be maintained. We've got 3 significant figures in each of those quantities, so we need 3 significant figures when we do our conversion. You can always round up at the end, but keep them the way they are to start with. So then the second step we have to do is we need to calculate our moles. You remember the formula for working out moles is the mass of the substance divided by its molar mass. So in this particular case, it'll be 0.04 divided by the molar mass of sodium chloride, which is just its atomic weight of 23 plus the atomic weight of chlorine, which is 35.5. And when we do that calculation, we come up with 6.83 by 10 to the -4 moles. Now we know how many moles we've got. We can substitute that into our formula to calculate the concentration. The concentration, you remember, is the number of moles divided by the volume. So we just put in our moles divided by our 0.325 litres, and that gives us our answer in moles per litre. So again, you notice that we have to worry about our significant figures. We only need 3 at the end here, so it's 2.10. Or if we do it in terms of molarity with the big M, it's 0.00210 molar solution. This problem is a little bit more complicated. In this case, we've been asked to calculate the mass of a solid that is needed to make up a particular concentration of solution. There are a number of quantities here. We've got volumes, we've got molarities, they've even given you a relative molar mass. So the first thing we can do here to stop ourselves from being confused is to actually write down what we know. The same way as we did with all those mass stoichiometry problems, we do it again here. Give the symbol, and that makes it much easier to see at a glance what you've actually got and what formula you actually need to work with. So C is our concentration, which is just 0.2 molar, and volume is the 250 mils, which we immediately convert into litres because we're working with a moles per litre solution, and we have our molar mass. All right, now just by inspection, if we want to calculate a mass of sodium carbonate, the first thing we're going to need to do is to get to our moles. And the only quantities we've got that will give us moles are that concentration and volume. So if we have a look at the formula, we know that concentration is equal to the number of moles divided by the volume, so we can turn that formula around to get number of moles as the subject of the formula, and that just means that we multiply the concentration by the volume to give us our number of moles. So in this case, we've got our 0.2, which is our concentration, multiplied by our volume, which is 0.25. And when we do that, we get 0.05 moles of our sodium carbonate. But we've been asked to turn that into a mass. So again, we need to pull up another formula this time, relating the moles to the mass. And that formula, you remember, is that the mass is equal to the number of moles multiplied by its molar mass. So substituting our figures in again, we already know our moles now as 0.05. Our molar mass is given to us, and so the mass of sodium carbonate we need is going to be 0.53 grams. Just as an aside from this, you see how the concentration of the solution is measured as 0.2 molar sodium carbonate? That means 0.2 moles of the whole sodium carbonate. So in that case, what's the concentration of our sodium ions going to be in that solution? Now, when you think about it, we've got 2 sodium ions per unit of sodium carbonate, so that's twice as many sodium ions. So therefore, the concentration of sodium ions in that solution is going to be twice as great. So it'll be 0.4 rather than just 0.2. Something to remember when we do some more calculations a little bit later on.